So hello. So my name is Sato from the RIKEN. Today I'm going to talk about is the FLAGSHIP 2000 project. This is the project to develop the Japanese flagship machine, supercomputers, which is the successor of the K computer. So as you know, we are going to use the ARM ISA. And we are expecting so much about the scalar vector extension for the HPC. So this is the outline of my talk. So first, I would like to describe the overview of our project. This is the development of the post-K machine, and including our work for the SVE. So, and today I'd like to present the recent our result from architecture research and compare research. So, first, okay. So, mission of our the project FLAGSHIP 2020 project is two things. One is the building the Japanese national flagship supercomputer we call the post-K, and also not only the hardware that we are going to develop the application softwares. So, and the project organization is like this. The RIKEN is in charge of development, and Fujitsu is the vendor partner. And application is developed by the many research institutions, and government is selecting the 9 the topics and funded to the 9 organizations to do the application program development for each the issues. So why that this project is called the FLAGSHIP 2020 is that machine development, machine installation will be happen in 2020. So here, right? So and we finished the basic design phase, and now is the design and the implementation phase. So, and as I said, we have decided to choose the V8 instruction set with the scalable vector extension. And now we are working for the detailed evaluation by the simulators and the compiler. So let me talk about what is the application for our machine. So the government is identified 9 issues for important the area. So first 2 is the related to the life and the medical things. And these 2 things is 2 issues related to disaster prevention and the global climate science, and the energy issues, and the industrial competitiveness. That is the including CFD and structure analysis. And last one is the basic science. And recently, the government is selected more project, more issues is shown in here. So, and first one is the related to social the agent simulation. And last one is the related to the AI and deep learning and artificial intelligence. So, so now recently, in HPC area, the co-design is become the very important keyword. So that is the design, hardware design, which is fitted to the application, and also application program should tune to the hardware. So in the early stage of our project, we asked each project to give us the typical application. So this application is called the target application. So using this application, we decide the number of similes and simile lengths and the cores and the caches, and also we examine the memory technologies and I/O network. So, and this table shows the target application we have used for the co-design, which is submitted by each application teams. So, and the program is from the MD application to the very basic science QCD application. So as you can see, there is many characteristics and many different motifs. So, and for example, Genomon is the genome processing application. This is they used to co-design the file I/O, and also NTCAM and LATK is the climate application and data assimilation. This application is much dependent on communication performance and memory performance, as well as the file I/O and the SIMD capabilities. So using these applications, we have designed our system. So, and the overview of the post-K. So I'm sorry, I cannot give enough information. So, but I will say that our system is the many-core based system. We don't use any GPU. So, and systems and total performance, we cannot say the peak performance because of our budget is not fixed yet. But officially, we are saying that the total performance should be the 100 times faster than the current K computer in some application. So, and the system software, so the RIKEN is also developing the system softwares, including the operating system. So MC kernel is the one of the software we are going to develop, and this is the lightweight kernel for the mini cores. So this is the very interesting the operating system, and it is very useful to avoid the jitters in the mini core system. And our team is developing PGAS language called X5MP, and another team is developing the DSL to make use of the SIMD. So, and post-K is designed by the Fujitsu, and the Fujitsu is you can see the Fujitsu is and we decided to use the ARM SVE. So, and the SIMD width is the 512 bit, and we are going to support the double precision and single precision and half precision. And the TOF interconnect is also used for the also post-K, but it is enhanced. So, and recently, for the ARM SVE, the FP16 half precision is supported for the ARM SVE. So we also think FP16 is one of the key, very important features for the future optimization, and also the artificial intelligence application like deep learning. So, and again, so it's the, according to our schedule, so this is the here, right? We are now in the middle, and our schedule is like this. So within 2019, the manufacturing and the installation will be happen. And in year of 2020, the installation and early access program is to be executed. So, and what we did and what we are going to do, for the ARM SVE. So, first of all, we did the early assessment of the ARM SVE specification, and after that, we are currently working for the Gen 5 simulators for ARM SVE. So, ARM company is developing also for the Gen 5 simulators, and they provide us the Gen 5 atomic mode, the source code, and based on that, so we are developing O3 mode, the simulators for the post-K. So of course, the Fujitsu have their own in-house processor simulators, which is very accurate to the hardware. So we are now is the adjustment of the parameters for performance to the Fujitsu the processor simulator. And using these parameters, simulators, we are currently doing the performance evaluation. And at the same time, we are doing the evaluation and testing the compiler. So we have the two kinds of compiler. The one is the ARM compiler, which is based on LLVM, and this is developed by the ARM compiler team. And Fujitsu is also have their own compiler, and they are designing and implementing their compiler for the ARM SVE. So, and we compare and evaluating the code is generated by the compiler. So, and but the code is still immature, so we have give the several feedback and taking a look at the code. So, and also we are doing the research using ARM SVE on our SVE. One of the research results, this is the result which is already presented in last week. It's the workshop is called the emergence of the vector architectures. This workshop was held in conjunction with the IEEE cluster conference. And please note that this research activity is independent of the development of the post-K processors. So our motivation is that how different is the performance depend on vector length. So SVE is very useful because the instruction set offer the vector length agnostic the programming. So this enables to run the same binaries on different the vector lengths. So, and why the FPU, the very long FPU is to improve the peak performance, but this is there is a trade-off between the amount of the hardware resources. So we would like to know what is the effect of the vector length under the almost fixed amount of the hardware resources. So for example, we choose the vector length 512-bit and 1024-bit. So how keep the resources size same? So for example, assume that we have the FP unit of 512-bit. So to execute the vector length of 128-bit, we can implement this wide of the vector length is by the 2 cycles. So these 2 things give the same throughput. So and also we can do the same things for the design of the raster file. So in case of vector length 502-bit, then for example we have vector length 96 various rasters, but to implement the vector length of 1028-bit, we can reduce the number of registers like this. So also we can implement the different vector lengths with the same throughput and the same of the amount of the hardware. So configuration we are thinking is that the length of 4, that means that 528-bit, and the length at 8, that means that the 1024-bit. So and with the same throughput and the same amount of hardware. In addition to this, we are thinking the double of the vector length, vector resources, and with the same FPU. So experimental setting is like this. So this is based on some hardware issues, but this parameter is very different from these of the POSIX processors. So and we are using the ARM CLang, the compiler, and we tested 4 kinds of the benchmark kernel: stream, streamad, and n-body, and the matrix multiply. So this is the evaluation result. So first, you can see if the triad, this is the throughput intensive and the memory bound application kernel. In this case, the performance is almost same. But we see the difference in n-body and matrix multiply. So and the performance is the similar. So vector length 8 is lower than the length 4, and the length of the 8 is faster than the length 4. So why? So the discussion is that why length 8 and length 8 is performance is different, and also the length 8 and faster than the length 4. So because while these FPU throughput is the same. So note that, so we are running the same source code, so vector agnostic program. So we examine the effect of the number of registers. This is the result of the n-body. And the horizontal axis shows that number of registers. So this is the ratio of the number of the physical registers. So you can see the vector 4 is the no difference, but length 8 is becomes faster when the number of registers is increased. So let me see what is the bottleneck. So we examine the resource full cycle in execution by the Gen 5 simulator. So, and this table shows that how cycles, what number of cycles these the resources became full. So you can see in case of the vector length 4, there is no register full cycle. That means that the changing the register is changing the register size has no effect. So, but in case of vector length 8, there is the much difference. So these column shows that this column shows the register ratio. So when increasing the number of registers, then you can see less register full cycle. So that means that if we have the small number of registers, we have the much the register full cycles, and it causes the performance degradation. And but if even when a vector length is 8, if we have the enough registers, the no register full cycles, that means that we can increase the performance improved. So, and this is the CPU utilization. So the efficiency of matrix multiply and the n-body can be improved by vector length 8, and also double size of the registers. So this is one summary. So wide the vector size over the FPU element size is improved the performance if there is the enough DNAME registers. And CPU utilization, FPU utilization also is improved. But this is a very, very preliminary evaluation. So we want to examine the out-of-order resources and the full optimized program, and checking another architecture parameters like fetch width and the number of cycles. And we are going to evaluate more large program, the application. So, and the next topic is that related to the compare research. So, and this topic result will be presented in IWOMP, which is held in next week. And we proposed the the more explicit the SIMD programming. So if you are familiar with the OpenMP 4.0, the much extension of the OpenMP SIMD directive. So, and if you write the programming is like this, that means that if this function is called a SIMD loop, then the compiler is automatically generate the SIMD code using this information. But generated SIMD code is not optimal in several times. So we propose the SIMD alias directive like this. So programmer gives the more variation of SIMD implementation of the large function like this. So this is the one of the example which is more fitted to the SVE. So this alias is specified using the specified kernel using the more the intrinsic function. So if compiler is matched to this pattern, then compiler can use this information to generate the more efficient code. So, and we compare the programming using the intrinsic the function is called C language extension. So this is the intrinsic specification. So, and this upper side is the programming using SLE. And if you can use the keep function, then we just specified the alias information here like this. So compiler is automatically expand these kernel loop to the almost equivalent program which is written in SLE. So okay, the conclusion. So I believe the SVE will deliver the high performance and flexible the SIMD vectorization to our post-K mini-core processors. And also, we think the establishment of the ecosystem in a high-end HPC is very important. And we are very willing to do the collaboration with partners and who are interested in SVE, as well as V8. So especially by sharing the experience of the compiler and simulator. So thank you for your attention.